Hey there, it's Shannon Magic Myers coming at you live from San Diego, California. Today we're going to be looking at division into cases and the Quotient-Remainder Theorem, which has a bunch of cool proofs associated with it. So let's do it. Think about what you've done in the past using long division many moons ago. If you have 20 divided by 6, what you're really doing, remember, is you're counting how many groups of 6 are in 20. So when we answer that, there are beautiful 3 groups of 6 in 20. And multiplying that, you would end up getting 18. And when you subtract, you get a remainder good of 2. So the 2 is our remainder. And the 3 here is our quotient. So just remember, what we are doing is counting these groups of 6. So what we have going on, is we have 20 units, right? 6, 7, 8, 9, 10, 20 of something, right, is our dividend. So here's one group of 6. Let's see, here's another group of 6, and then another one. And we've got our 2 remainder, right, up here. Hopefully that wasn't too low for you. And we have our 2 remaining. So now those are the 2 that we used for the remainder, and the 3 groups we circled were the 3 groups of 6 that are the quotient. So we can actually write 20 as the divisor, 6, times the quotient, which we got is 3, plus 2, which is our remainder. So this is our D. This we can call our N. The 3 was our quotient, and this 2 was our remainder. So let's check it out, the Quotient-Remainder Theorem. We'll use this as proof for, or as a tool to prove other theorems as we go on in this section. So given any integer n and positive integer d, there exist unique integers. So uniqueness is one important part of the theorem. Q and R such that n is equal to some divisor times some quotient plus a remainder r. And, well, since your remainder can't be bigger than your divisor, what we need to do is have a bound on it. So you could have a remainder of 0. That means that your divisor was a factor of the dividend, but you don't have to. It can actually range as any positive integer between 0, where it includes 0, and what? D. Cool so far? Awesome. All right, so we'll be covering the proof for, I think, the uniqueness parts in chapter 5, and then in a later chapter we'll do the other portion. But just to get sort of a big picture idea, if you make a couple number lines, all right, I mean, the positive end is pretty easy to see. Got a number line, I don't know, started at 0. Of course, you've got numbers going to the left of 0. But let's say, this is 1D. Here we have 2 Ds. And then etc. until you get to some amount of QDs, right? That's how you get that quotient. But there ends up being some spot where, n might end over here. Notice that's purposely a little bit less than your divisor, whatever it may be. And so what lies here is our what? Remainder. Cool so far? All right, so on the other end, what you'll have is something along these lines. Now you got to be careful because Q can be positive or negative, while the numbers or quantities Q and, Q can be negative, N can be negative, but our divisor is set to be positive, all right? So if there was a negative, we'd assign it to N. And our remainder is positive. So you're going to be adding a positive integer as your remainder. So therefore, you're going to have to go past N on the negative side in order to, when you add that positive integer, get back to N. So what does this look like? All right, well, let's say we've got, we'll go start on this side. So this is 0. You've got stuff on the positive side. And then you're here at negative 1D. And then you're at negative 2Ds. And then you keep going, right? Here's like a negative 3D. You keep going in this manner, and you're going to hit your N, all right? So N is going to be, I don't know, call it somewhere over here. And then Q, remember, can take on negative values. So what we're going to do is we're going to have Q times D be somewhere over here. So, again, what do we get over here? That ends up being our positive remainder R. Whoops. I was doing that in green, wasn't I? Okay, cool so far? Moving right along, let's do a couple of examples, all right? So in these, we just want to write them in the format where we've got N is equal to D times Q plus R, and remember that R and D are set to be positive, and R could be 0 as well. So, all right, in this one, 44 equals, our divisor D is 15, and we want to write this as a product plus some remainder, right? So 15 times, beautiful, 2 gives us 30, and then when we add 14, that's our remainder. So this one is our N, this was D, this here is our Q, and the 14 is our remainder. Groovy? All right, so N is negative 111. So we have negative 111, right? That's equal to, well, 4 is our divisor. So 4 times what? Remember, we got to go just a little bit past the negative 111. So Q is going to end up being negative, isn't it? So try a few numbers, and you'll find you'll get negative 28, right? And that negative 28 times 4 is negative 111. So when you add 1, it brings you to your 4 times negative 28 is negative 112. So when you add that, you'll get back to your negative 111, which you needed. All right, so this negative 111 is N, 4 is our divisor D, negative 28 is Q, and then 1 is R. All right, so next up, 84, and then with a divisor of 7 times, beautiful, 12 is actually exactly 84. So if we want to write it in that format, we would have a 0 remainder. We just add 0. So 84 is our N, 7 is D, 12 is Q, and then R is 0. Groovy? Okay, Now be careful. Don't switch things just to make them work. 12 is less than 24, isn't it? And they're both positive. So basically, there are 0 groups of 24 in 12. And then we'll have a remainder of 12. So 12 was N, 24 was D, Q is 0, and good. This 12 represents the remainder. Groovy? All right, so definition. Given an integer n and a positive integer d, n div d, I'm not sure if I'm saying that right, but just bear with me, I'm not a coding girl. N div d is equal to the integer quotient obtained when n is divided by d, and n mod d is the non-negative, so that means it can be positive or 0, integer remainder obtained when n is divided by d. So the takeaways from here is that n div d is equal to what? Very good, Q, and mod d is equal to R. So symbolically, n div d equal to Q and n mod d equal to R. Very good. If and only if n is equal to d times q plus r, where q and r are integers and 0 is less than or equal to r is less than d. Cool, cool? Okay, note that n mod d must be one of the integers from 0 to, beautiful, d minus 1 inclusive. So on the calculator, to find n div d, all you need to do is divide n by d and ignore any numbers to the right of the decimal. To find n mod d, use the fact that n is equal to d times q plus r. Isolate r to get n minus d times q, and then substitute in n div d for q. All right? So at the end of the day, you would get r is also equal to n minus d times n div d. Groovy? All right, so next up we have, let's compute these guys, 16 div d and 16 mod 5. All right? So, all right, what do we know? We know that n div d is q, right? N mod d, and yes, you need to remember these things, is equal to r. And we also know that n is equal to dq, I remember that from Dairy Queen, dq plus r. And what else do we know? We found out that r was equal to n minus d times n div d. Okay? So, computing div and mod, well, if you do this one, remember that if we start out with our n equals dq plus r, 16 is equal to, awesome, 5 times what? Awesome. 3 plus 1. So, what is 16 div 5? Perfect. It's 3 because you're looking for the Q. Now, that's one of our results. Our other result would be looking for 16 mod 5, right? So we did the work already. So 16 mod 5 is that integer remainder you get after dividing 16 by 5. And what was our remainder? Beautiful, 1. So 16 mod 5 is 1. Now on the calculator, if you need to see it, what we can do is just go over here, and where's my calculator? Here we go. So if I clear this, what you would do is you just take your n divided by your d, which was 5, enter. Notice you get 3.2, so you're just going to be looking at the 3. That's your answer for that one. And then to get r, you would do that n minus d times n div d. So n was 16 minus what? D, which was 5, and then times what was n div d? 3. Cool so far? And that gave us 1. Perfect. I think there's also somewhere a way to do like your integer only. Let's see, I'll look for it just for a second. I don't think you really need it that much, but it has an I. Math. Oh, I part, integer part. So let me try that. Integer part of 16 divided by 5. Oops. That was not good. Let me do second entry and come back here, and that should have been divided by. Oh, and look, you get the 3. So you can also do I part, and I found that under math and then number. Or you can just put in, the formula we derived for R. All right, so here's the picture. I scratched out the one where I made an error on the graph or on the input. So that I part 16 divided by 5 gives you just the integer part. That's what the I stands for. If we were going to do this next problem, well, negative 38 div 4. Well, what are we going to do? Remember, n equals d times q plus r. This is my n. 4 is the d. Remember, you have to go past this one because it's negative. So 4 times, beautiful, negative 10, and then plus 2. So just double check. 4 times negative 10 is negative 40. You add 2 to that, you get negative 38. So we're good to go. Negative 38 div 4 then is equal to, good, negative 10. And negative 38 mod 4 is that remainder, which is 2. Cool, cool? All right, so you can see how to do that on the calculator. I won't redo that one. I think you're very skilled at that kind of stuff. And I will move it on. All right, so example 3, January 1st, 2000 was a Saturday, and 2000 was a leap year. On what day of the week will January 1st, 2050 fall? Well, leap years occur every 4 years, and they have 366 days. Regular years have, good, 365 days. So the first step would be what? Find the number of leap years in this range. Well, we want to include that first one, the 2000. So in order to figure that out, I'm kind of thinking that maybe we ought to go back to 1996, find the range, and then divide that by beautiful 4 because the leap years are every 4 years. So 2050 minus 1996 is equal to, good, 54. And 54 is equal to 4 because there's leap years every 4 years. And then times what? 12, I think, or let's see. No, 13, right? Times 13 gives us 52, and then plus 2. So at the end of the day, there's 13 leap years. That's the number of leap years. And if you include the year 2000 and you count up to 2050. Or you could have just counted every 4, whatever you want to do. All right, so next up, we need to figure out what? Well, we probably want to find number of days, right? So that's not so bad. There's 13 leap years. So the number of days that we're looking at is, good, 13 times 366 plus, now we're starting again, going from 2000 to 2050, right? So there's 50 years in all. 50 minus 13 is, great, 37 times 365. And what is that equal to? I got, what did I get? I got 18,263. Cool so far? All right, so now we have the total number of days that will pass between January 1st, 2000 and January 1st, 2050. So what do you think we ought to do next? I mean, doesn't it matter what day that January 1st, 2000 fell on? Because you have 7 days in a week. So that should tell you that D is great, 7. But what else might we want to do? We might want to do a little bit of a code, right? So let's just code the days so that we get in on the right day. We don't want to like start on a Sunday, right? We don't know. So because this happened on a Saturday. So if we code the days and we call this the day, and then we'll just say code, we'll make a numeric code. Then we'll have, we can call Sunday day 0, right? We could call Monday day 1, Tuesday day 2, Wednesday day 3, Thursday day 4, Friday day 5, and then Saturday would be day 6. Cool so far? Awesome. All right, so we've got that going on. Now we just need to use our mad number theory skills, right? So we have a bit of an offset, don't we? Because we've coded Saturday as day 6, right? So why don't we do this? I mean, the total number of days that we're going to need to divide are going to be what we started with, right? So we need to figure out our mod expression, right? Because what we're really looking for is the remainder when we divide the total number of days plus our coded day by 7. So what we want to figure out our n mod d. Well, our n is going to be the number of days that are in that range of years, plus the day we're starting on. So we're starting on what we've coded as day 6. And so that's going to be 18,269. Well, we know that D has to be 7 because there's 7 days in a week. So now all we need to find is 18,269 mod 7. And we'll get the remainder, we'll get the R from that. And what's going to happen? We'll have what day of the week, right? So we'll just keep that blank for now. The way we can figure that out is what? We need to write 18,269 equal to 7 times something, right? Plus a remainder. So what is that something? 7 goes into 18,269. Let's see, 2 would give us 14, and then 52 would be, or 42 rather, would give us 6, 0, and then 7 goes into 69 9 times with, good, 6 remaining. So guess what? We get 6. So 18,269 mod 7 is 6, and 6 represents Saturday. So let's give our conclusion in words. Oh, sorry, this should have been number 4. So we'll call number 5 our conclusion. And our conclusion is that January 1st, 2050 falls on a Saturday. Isn't that a groovy application? I liked it. All right, so let's go ahead and get to our next theorem. This is a theorem involving parity. Parity means that you've got odd and even. And so opposite parity means that if one is odd, the other would be even, or vice versa. So any 2 consecutive integers have opposite parity. So let's check it out. Proof, gotta start somewhere, right? So why don't we let m be any integer? Well, what will the next consecutive integer be? You'll just be adding by 1, right? So we'll write that in. M plus 1 is the next consecutive integer. All right. Aren't there different cases? I mean, you could start out with an even, or you could start out with an odd. So this is where we get into division by, or proof by division into cases. So case 1, why don't we let m be even? Well, don't we know the definition of even in math? I mean, there must exist what? Some k that belongs to the integers. You can call it whatever you want. K is just a typical one that is used. And such that m is equal to twice k. All right, well, what's m plus 1 going to be? M plus 1 would then be 2k plus 1 by substitution. And what is 2k plus 1 by definition? Odd. And we'll say that is true by definition. Okay, so here we go. Case 2. If we start out where m is odd, then there exists a k belonging to the integers such that m is equal to 2k plus 1, right? That's by definition. So what are we going to get for m plus 1? That will be 2k plus 1 plus another 1. And that's just by substitution. I guess I should have said definition here and here maybe. And then, all right, so now this is equal to, using some algebra, 2k plus 2. And then aren't the set of integers distributive? So we end up with 2 times k plus 1. So now all we have to do is we have to show that k plus 1 belongs to the integers, because then we know we have an even. Well, k plus 1 belongs to the integers, and that is just by closure. When you add 2 integers, you get out another integer, right? And we could say thus 2 times k plus 1 is even. And guess what? We're done. We showed both cases. If you start out with an even, your next integer is an odd. If you start out with an odd, your next integer is an even, so they have opposite parity. All right? Okay, so next up, method of proof by division into cases. So we just did this, but let's fill in, what the steps were. To prove a statement of the form, if A1 or A2 or ... or AN, then C. Prove all the following. You got to prove every case. So if A1, then C. If A2, then C. And then all the way down to if A sub n, then C. This process shows that C is true regardless of which one of the cases you're on. So it could be A1, A2, all the way down to A sub n. Happens to be the case. All right, so this next theorem is another kind of cool one. The square of any odd integer has the form 8 times m plus 1 for some integer n. So let's check this bad boy out. When we do this proof, suppose we have some n, and this n could be any integer. It's arbitrary. So why don't we let n equal to 4q plus r such that 0 is less than or equal to r is less than, what do you think? 4, because we had let n equal 4q plus r. All right, so far. And q and r belong to the set of integers. Okay, so far. Now, 4q plus r can be represented as 4q. That's if you have a 0 remainder. 4q plus 1 if there's a remainder of 1. 4q plus 2 if there's a remainder of 2, right? Oh, there's one more, sorry. Or 4q plus 3. And this is due to that cool theorem about the Quotient-Remainder Theorem, which is number 4.4.1. Alrighty, so since n is odd, n must be equal to what? Remember, I think we did this in another lecture. We showed that if you 2 times 2q, wouldn't that part of it be even? So if you're adding an odd to that, you'll end up with an odd. So n has to just be one of 4q plus 1, or n could be 4q plus 3. Good so far? All right, so the first case, and if you're interested in that, the reason I chose 4 as the divisor is because of this 8 right here. That 8 showed me that if I squared, right, because we're going to be squaring n, if I squared that, I wouldn't be able to divide out an 8, and that's what you're going to have to do. That's the evil plan for these. So that's why I went with the 4, and there's something called modulo 4, and it's in the book. It has a good example in the book, so you can take a look at that. I think it's example 4.4.6 on section 4.4, but that is why I chose the divisor of 4. Okay, so case 1, right? Let n equal to 4 times q plus 1. So if we square both sides, do you see we'll have n squared is equal to quantity 4q plus 1 squared. Well, if I complete out the square of that binomial sum, I will get 16q squared plus 8q plus 1. And remember, the whole plan is that I'm going to be using that theorem 4.4.1. I want to show that whole deal about n is equal to 8 times some integer plus the remainder 1. So let's check it out. Here we go. So if I factor out an 8 here, then I will have q squared plus q. And I still have 1 hanging out, right? So now I just need to show that q squared plus q belongs to the integers. So q squared plus q belongs to the integers. And why would I say that? Good, by closure. Okay, so far? Good. Thus, n squared equals to, oh, actually, let's let m equal to q squared plus q. Thus, n squared will equal to 8 times m plus 1. And that's what we wanted to prove, so we can check off that case. All right, so for the next case, case 2, why don't we let, again, n be equal to 4q plus 3 this time? Those were the possibilities. So we're going to have n squared is equal to quantity 4q plus 3 squared, which will give us 16q squared plus 24q's, this is all just by algebra, plus 9. but can't we break up that 9 into 8 plus 1? Because I need to factor out an 8, right? So 8 times 2q squared plus 3q plus 1 plus another 1 is what I get. Groovy? All right, so now letting m equal to 2q squared plus 3q plus 1, it belongs to the integers. And why? Awesome, by closure. If you multiply or add integers, you get integers back for your result. So what will happen is n equals to 8m plus 1, and that's what we needed to show. So we're all done. Groovy? Now we move on to the definition for absolute value. So we have, for any real number x, the absolute value of x denoted, you got the bars there around x. So absolute x is a piecewise function, and it equals to x for x greater than or equal to 0, and the opposite of x for x less than 0. So we're going to show that we're doing this definition and a couple of lemmas so that we can do this really kind of cool proof for the triangle inequality, which you'll actually learn more about when you're in linear algebra. All right, so let's do it. Lemma 4.4.4, for all real numbers r, negative absolute r has to be less than or equal to r, which in turn is less than or equal to absolute r. So this one completely will, for the most part, it uses the definition from above. So starting our proof, if we let r belong to the real numbers, r can either be greater than or equal to 0 or less than 0. So the first case, we'll let r be greater than or equal to 0. So r is greater than or equal to 0. And what does that mean? Well, by definition, absolute r is just going to be r and let's see what else we have going on. So you've got a positive number for r, positive integer for r. So wouldn't that imply that negative absolute r would equal to negative r, right? Because r is positive. So we'll just write negative r. And that must be less than 0. And negative absolute r would also be less than, if r is positive, wouldn't the negative of absolute r have to also be less than r, right? So what do you think? I think we showed it. Thus, negative absolute r is less than or equal to r, which is less than or equal to absolute r. Okay, so second case. R is now less than 0. It's a negative integer, right? So by definition, the absolute value of r will be negative r, because you get a positive out, right, for when you evaluate an absolute value. And so if it's negative inside there, it's switched its sign. So sometimes it's a little confusing. So multiplying by -1 on both sides, what are we going to get? We'll have -1 times absolute r would equal to -1 times -r, just using some algebra. And this brings us to negative absolute r is equal to r. So therefore, okay, so since r is negative, right? We know r is negative. We'll just say it again. R is less than 0. And we also know that absolute r is definitely positive, right? Greater than 0 or 0, right? It follows that r has to be less than absolute r. So we have negative absolute r is less than or equal to r is less than or equal to absolute r. So it holds for both cases. We're all good. All right, so next up we have another lemma. For all real numbers r, absolute -r is equal to absolute r. So let's look at our proof here. Let r belong to the real numbers, right? So we're going to use a few things from algebra, namely one of them that if r is greater than 0, negative r is less than 0. Remember, you have to switch that inequality. And if r is less than 0, negative r is greater than 0. So let's see what we have. We want to take a look at what does absolute -r give us. So using definition of absolute value, we have -r is going to be what? Oh. The absolute value of -r is going to be itself for what? -r greater than 0. It's going to be 0 for r equal to 0. And it'll be opposite -r for -r less than 0. Cool so far? So that, of course, is by definition. So now, all right, well, using some algebra, absolute -r is equal to the same, the first two will be the same, -r for -r greater than 0, 0 for -r equal to 0. Sorry, that first one should have been -r equal to 0. And then just r for -r less than 0. But using those properties from algebra, what will happen? We'll end up with absolute -r will be equal to -r for r less than 0, 0 for r equal to 0, and r for r greater than 0. So I just basically multiplied these guys each by -1 on both sides. So, all right, cleaning that up a little bit, absolute negative r is going to be r for r greater than 0. It will be, and actually, or equal to, we can put these two together, and then it'll be negative r for r less than 0, right? Because it'll just be itself, right? So that's from the top. So now, but what is this definition? Well, on the right side, it's the definition for absolute r. So we're all good. We showed it. So if you want to write anything, these here were, properties from algebra. This is just rewriting, cleaning it up. And then this is by definition of absolute value. Cool, cool? All right, so now finally, drum roll, we get to the triangle inequality. So again, in linear algebra, we're going to be looking at this in terms of vectors. There's a really cool proof on that. But for now, we're just going to use the some stuff from algebra and also one or two of these lemmas. So the triangle inequality says for all real numbers x and y, absolute x plus y must be less than or equal to absolute x plus absolute y. All right, so starting our proof, let's see what we have. We're going to let x and y be any real numbers. So what possibilities do we have? X plus y could be positive or 0, that's some, or x plus y could be negative or less than 0. So if we do our first case, that x plus pi is greater than or equal to 0, what do you think? Well, absolute x plus y would equal to x plus y. And so from that first lemma, 4.4.4, okay, it actually gives us that x needs to be less than or equal to absolute x and y is less than or equal to absolute y. And that was from lemma 4.4.1. All right, so hence, oops, sorry. Absolute x plus y, which is equal to x plus y, must be less than or equal to absolute x plus absolute y. Second case. Well, what if x plus y is less than 0? Well, absolute x plus y would then be the opposite of quantity x plus y, right? By definition, which in turn is negative x plus negative y, bringing that negative through the quantity. So we have what? well, negative x is going to be less than or equal to absolute negative x. But what did we say absolute negative x was? Beautiful. Absolute x. And same with the y. Negative y would be less than or equal to absolute negative y, which is equal to absolute y. So, absolute x plus y is going to be less than or equal to absolute x plus absolute y. And we're done. We showed both cases. Cool, cool? All right, so now a couple of examples. So suppose b is an integer, and if we have that b mod 12 is 5, so the remainder when b is divided by 12 is 5, okay? We want to know what is 8b mod 12. So let's just start it out as a proof because it wants us to, this problem asks for us to prove it. So let's think. Let b be an integer, right? Because that's a requirement for that portion of the mod. And such that b mod 12 equals 5. Good so far? Now, by theorem 4.4.1, we know that b has to equal to 12q plus 5 for some integer q. Cool so far? All right. Well, let's work with that. So b equals 12q plus 5, right? If I multiply both sides by 8, because I need that 8b, I'm going to get 8b equals 8 times quantity, 12q plus 5. So, continuing, we will have 8 times 12q plus 40. Cool so far? I have to work on this a little bit more because I have a remainder of 40 as it stands, and my divisor, remember, is good, 12. So let's work with this a bit. 8b equals, the integers are commutative, so 12 times 8q, right? And then, all right, 12 times, I'll just write it out, times 8q plus 12 times 3 is 36, right? So couldn't I write 40 as 36 plus 4? So now, factoring out a 12 from the first two terms, I would have 12 times 8q plus 3 and then plus 4. Cool so far? Now, if we let k equal to 8q plus 3, k belongs to the integers from beautiful closure properties. So that gives us that 8b is equal to 12 times k plus 4. Thus, (8b mod 12) equals, good, 4. And we're done. Pretty cool, huh? All right, next example. prove for all integers m and n, if m mod 5 is 2 and n mod 5 is 1, then m times n mod 5 is 2. Okay, kind of similar, except you've got two different mods going on and you want to know the product. So, proof. Well, we got to lay everything out, right? You have to lay out all your tools and show that they're from the proper areas. So if we let m and n belong to the integers such that m mod 5 is 2 and n mod 5 is 1, because that's all given. So, okay, there must exist. We're gonna have to come up with two more integers, right? Because we're gonna rewrite them in that other format. So let's just use a and b, and a and b that are integers, such that m is equal to, well, the divisor's 5, right? So it'd be 5a and the remainder's 2, so plus 2. And n, therefore, would be equal to 5b plus 1. That, my friends, is again utilizing theorem 4.4.1. All right, so let's see what we've got going on. M times n is going to equal to, by substitution, what was m? Good, 5a plus 2 times 5b plus 1. So I'm just substituting what we found, m to be equal to and n to be equal to. So, all right, continuing, let's see what we have. Square or multiply it all out. So just use some algebra properties. So I'll have 25ab, let's see, plus 5a plus 10b plus 2. Now, remember that both of these guys have 5 as the divisor. So, okay, I want to bring out that 5. So, this will leave me with 5ab plus a plus 2b, and then I still have the plus 2 hanging out. So, all right, why don't we let k equal to 5ab plus a plus 2b. K belongs to the integers because of beautiful closure properties. If you multiply integers, you get an integer. If you add integers, you get an integer. So, what are we going to have? Well, we might also want to say and 0 is less than or equal to 2, which is less than 5, our divisor, right? So what do we end up getting? Well, m n mod 5 is equal to 2, and that's again by theorem 4.4.1, which is that quotient-remainder theorem. Groovy? All right. So our last problem of the of this section. So this one here, use the quotient-remainder theorem with d equal to 3 to prove that the product of any two consecutive integers has the form 3k or 3k plus 2 for some integer k. And then we want to rewrite our results in the mod notation. So let's get started. Proof. Let m belong to the integers. Right? So, I don't know. What has to be true? M and m plus 1 are consecutive integers. So we'll be using this for all of the cases. And what else do we know? What else do we know? Well, there has to exist some Q and R which belong to the integers such that m is equal to 3q plus r. And that, of course, is by theorem 4.4.1. All right, so now let's see what we have going on. R can equal to 0, 1, 2, or just 0, 1, or 2 this time, because since 0 is less than or equal to R, which has to be less than 3, since our D equals 3. Well, what do you think? Let's do our cases. So for the first case, we can let R equal 0. So letting R equal 0, what's going to happen? M will equal to 3q plus 0, which is just 3q. Good so far? So now doing the m times the m plus 1 will give us 3q times 3q plus 1. And that's just by substitution. All right, well, doing a little bit of algebra, right? And remember, we have a divisor of 3, don't we? So we want to keep a 3 out there. So this is 3, and then we would have a 3q squared left, right? Doing some algebra. And then we would have plus another q. Good so far? All right. Well, let k equal to 3k squared plus q. K belongs to the integers because of the closure properties for multiplication and addition. And m times m plus 1 is just equal to 3k, which is part of what we wanted to show, that it could take on values of either 3k or 3k plus 2. So we're good on that case. We can check that one off. So now let's go to case 2. So for case 2, we're going to let r equal to 1. So that means m's going to be 3q plus 1. So m times m plus 1 will be 3q plus 1 times 3q plus 1 plus another 1. Groovy? And that's just by substitution. So, what's next? Good, let's clean it up a little, right? This time I'm just gonna combine these. It's a little more complicated. And then use some algebra to multiply out these binomial sums. So we'll get 9q squared, and then plus 9q's plus 2. And remember, we want that divisor of 3. So I'm going to factor out a 3 to the first two terms, and then we'll be left with 3q squared plus 3q, and then we have a plus 2 hanging out. So if we let k equal to 3q squared plus 3q, k belongs to the integers because of, you got it, closure, and what else? M times m plus 1 is going to be 3 times k plus 2. So that's case 2 shown. All right, so the last case that we need to go through is when what? Let r equal to 3. So r has to equal to 2, my bad. So m will be equal to 3q plus 2. So m times m plus 1 will be 3q plus 2 times 3q plus 2 plus another 1. And that is by what? Great substitution. All right, so this in turn will equal to, cleaning it up a bit, 3q plus 2 times 3q plus 3, which is 9q squared plus 15q plus 6. Factoring out of 3, we'll have 3q squared plus 5q plus 2. And look, it looks like this one won't have a remainder. So what do we do next? We let k equal to 3q squared plus 5q plus 2. K belongs to the integers because why? Closure properties. And m times m plus 1 is equal to 3k. So we have shown all 3 cases and we're done. And we're done with the lesson. So I hope you guys have a wonderful morning, afternoon, or evening. If you like what I'm doing, please subscribe. And